So we have seen maximum likelihood decoders. We have investigated maximum likelihood decoders for the special case of the binary repetition code. And now we're going to see what are the performance limits that we can achieve with an ideal maximum likelihood decoder and some particular codes. So it's very difficult actually to determine the theoretical performance or the performance of any code with a maximum likelihood decoder. That's something that depends strongly on the code, but we're going to look at one very particular code, which is a so-called random code. That's what we're going to do in this subsection of this chapter. So what we want to start with is would like to analyze the performance of maximum likelihood decoding. The question we ask ourselves, two questions. First question we ask ourselves, we have a given channel and we want to allow a certain probability of error PE. We have a probability of a decoding error PE. What is the largest rate that a code can have? That's the first chance. So we have a certain channel. We can tolerate a certain probability of error, once that depends on the application. And then would like to maximize the rate, because maximizing the rate means we maximize the data information. Second question, that's a natural follow-up question, is if we have a code of rate R, then for a certain channel, what is the lowest decoding error probability that we can achieve with maximum likelihood decoding? The first question is more from a system designer's point of view, who wants to maximize the information throughput. Second question is more if we have a certain code that is already implemented and a certain channel, what is the smallest probability of error that we can achieve? As I said, these questions are not very easy to answer for specific codes. And in fact, they turn out to be very difficult to answer. And they turn out to be that difficult to answer that we essentially today cannot answer because it's an NP-hard problem. And we would need to have supercomputer, and even all the supercomputers that we have at our disposal at the world are not sufficient for simulating or calculating the error probability of maximum likelihood. So what we need to do is we need to use a trick. So the trick that we use, the trick that has been introduced by Claude Shannon, said if we cannot investigate the performance for a specific code, then let's see if we can construct a random code, and then we can use the toolbox of probability theory. It's a very powerful toolbox of probabilities, and we use this toolbox to hopefully simplify the problem. So we use a code that is randomly constructed, and this is called the random code. That's something we'll see all the time in this subsection. What is a random code? The random code is something that is very simple. So we saw the definition of a code, C of length n, with m equals 2 power k code words. That's essentially a set of vectors x1 up to xm. And each of those vectors is a binary number, a binary vector of length n. So what we do is, for each letter xji of a code word xi, we make a random experiment. So we have a set of channel input symbols x, and we know that the cardinality of the set x is equal to v, and we just choose each letter of the code word xi with uniform probability. So we say that the probability that letter j of code word xi, that this one is equal to k, is 1 over v. Usually x is, so usually, and that is especially in our lecture, v is always equal to 2. So essentially what we do is we take a coin, a pair coin, and we flip a coin for each letter of each code word. So we flip a coin. If it's heads, we take a 0. If it's tail, we take a 1. That's it. So that's how we construct the code words. And it depends a little bit how we choose this distribution. And we will see later that depending on the channel, different distribution may be better. So this is the uniform distribution. And for the time being, we can just stick with the uniform distribution. But we will see later that this uniform distribution may not be the best choice for many channels. And then we can change this distribution. But that's the way we choose the code. So essentially just many random experiments, and then slowly we build up our code book, our code. So first we make n random experiments to choose code word x1, then we make n random experiments to choose code word x2, we make n random experiments to choose code word x3, and so on. So that's how we proceed. That's how we're going to proceed. So essentially a very simple construction. Note that we may be unlucky and we may choose 2 times the same code word. That's okay. That's not prohibited by this code. The code may have minimum distance of 0. We don't care. We just strictly follow the scheme. It's like a recipe. We have a recipe and it tells us exactly how to choose the code words, and that's how we follow it, and that's what we do. That's how we can construct the random code. So this is the code that we have, the random code, and this random construction will help us later simplify our error probability calculation. So that's very important that we use such a random code. So before we dive into the analysis, we need a few preliminaries that you may know or you may not know. And let's start to look at it. The first one we will need is the Markov inequality. You will actually know if you did your bachelor at KIT and if you had the probability theory, Wahrscheinlichkeitstheorie lecture, you have met the Chebyshev inequality. The Markov inequality is a weaker inequality. Actually, the Chebyshev inequality follows from the Markov inequality. The Markov inequality is simpler than the Chebyshev. So the Markov inequality is a very simple one. It's also very simple to prove. So essentially, it is we start with a random variable x, and it's important that x is non-negative. So x is a non-negative random variable, and the mean of x should be finite. So then we fix some value alpha larger than 0, and we calculate the probability that x is larger or equal than alpha is upper bounded by the expectation of x, the expected value of x, divided by alpha. So we have a non-negative random variable, so x can only take on values larger or equal than 0. And we're looking at the tail probability, so the probability that x is larger than alpha, so at the very end of the distribution. That's smaller or equal than the expectation of x divided by alpha. Looks like magic, but we can essentially prove it in one line. So here is the proof. We start with the expectation of x. So we start from this side. The expectation of x, the definition is the integral from minus to plus infinity of x times f of x dx. And we know that x is a non-negative random variable. So here it's important, A is because it's non-negative. So what we have is the we can rewrite this as the integral from 0 to infinity of x times f of x dx. Non-negativity means that f of x is 0 for x being negative. So therefore we can write the integral from 0 to infinity. So then what we do next is we subdivide this integral into two parts. We first look at the part from 0 to alpha and then the tail from alpha to infinity. So we write this as integral from 0 to alpha, x times f of x dx, plus the integral from 0 to infinity, x of x times f of x dx. And now we just assume, or we just say this whole expression is larger or equal than just this expression. So we know that this part is larger or equal than 0 because x takes on a value between 0 and alpha. It's clearly larger or equal than 0. And f of x is a probability density function. And by definition, a probability density function is always larger or equal than 0. So this part is larger or equal than 0. So we can just ignore it and say this whole thing is larger or equal than just the second part. So and in the second part, again, we can simplify. So x goes from alpha to infinity. So x essentially is larger or equal than alpha. So what we can do is we can just replace x by alpha and put an inequality, further inequality sign here. So this is larger or equal than alpha times f of x dx. And now, of course, the alpha, we can put it in front of the integral. And we are ending up with the integral from alpha to infinity, f of x dx. This is alpha times the probability that x is larger or equal than alpha. And that's essentially the proof. So then we can just rearrange, we divide by alpha, and then we get the statement of the Markov inequality. So the Markov inequality looks to be very weak inequality, but it turns out to be very powerful in many cases. So we can also prove it for discrete random variables. So here is an alternative proof for discrete random variables. So we start with the probability that x is larger or equal than alpha. This is the sum over all x larger or equal than alpha. That probability that x is equal to x. And we can replace this with the indicator function. So this is the indicator function that x is larger or equal than alpha times p of x dx, p of x being equal to x, and summing up over all alpha. So if you don't know the indicator function of some event E is equal to 1 if E is true, and 0 if the event E is false. So if x is larger or equal than alpha, this indicator function returns 1, and otherwise the indicator function returns a 0. That's also given here again. So now the indicator function looks like this. Now we make a very neat trick. So we have x, and we have the indicator function that x is larger or equal than alpha. And this indicator function looks like this. So we have indicator function. I'm using a collar. So it is 0 up to some point alpha, and then it jumps to 1. So this is the plot of the indicator function. And what we can do now is we can say that the indicator function is bounded by this linear function. So this linear function is f of x equals x divided by alpha. And we see that f of x equals x divided by alpha is larger or equal than the indicator function that x is larger or equal than alpha. So they touch each other exactly at 1 and at 0. And again, we know that x is non-negative. So as we defined, x is a non-negative random variable, so it can only take on values larger or equal than 0. And in this case, the inequality holds. So we can bound the indicator function with x divided by alpha. So you can say that the probability that x is larger or equal than alpha is upper bounded by the summation over all x of x divided by alpha. And this is, when we move alpha outside of the sum, this is the definition of the expectation. So if we take a look, this guy is the expectation of x. The expectation of x divided by alpha, and we have proven the theorem. So this is the Markov inequality. Let's look at an example of the Markov inequality. So usually not a very good bound. So let's look at an example. So we look at x is the height of an average male German person. So this is very well tabulated. We have the heights of the people, and we can average by country. So I took the source from Wikipedia, the average human height by country. And x is clearly a non-negative random variable. A human cannot have a negative height. So we always are larger than 0, taller than 0 centimeters. So x is a non-negative random variable, the average height of a male person, and it turns out to be 175 centimeters. So now let's look at the probability that a person is taller than 3 meter 50. 3 meter 50. I have never encountered such a person. And I don't believe such a person exists according to Guinness Book of World Records. But let's see what the Markov inequality tells us. According to Markov inequality, the probability that a male German person is larger or equal than 3 meter 50 is upper bounded by the expectation of x divided by 3 meter 50, so 1/2. So according to Markov inequality, we have a statement saying that the probability that a German male person is taller than 3 meter 50 is less than 1/2. It's not a very insightful statement. So I don't think this is useful in practice, at least for this random variable. But it will be very useful in our case. So that's the Markov inequality. What we need as well is something that you also probably know, and if not, this is a very good refresher. That's the union bound. So the union bound says that if we have two events, we have an event A, for instance, the event that the random variable x is larger or equal than 0.3. It's what we call an event. And we have another event that we call B. So then the probability that either the event A or the event B holds, so it's the union of A and B, is equal to the probability that the event A holds plus the probability that the event B occurs minus the probability that both events A and B occur at the same time. This probability, of course, is larger or equal than 0, and this probability is usually very difficult to calculate. So we just remove it and say this is smaller or equal than the probability that event A occurs plus the probability that event B occurs. So we can draw this using a Venn diagram above. So let's take a look. we have the probability that event A occurs. That's event A occurs for certain outcomes. Then we have an event B. So the probability that event A occurs is this. So this is the probability that event A occurs. The probability that event B occurs is this. And here in the intersection, this is the probability that event A occurs and event B occur at the same time. So now we see that if we want to count the probability that event A or B occur, it's the probability that event A occurs plus the probability that event B occurs. But now we counted, this part we have counted twice. It's already included in P of A and it's included in P of B. So we need to remove it once. And that's what we do here. We remove it once. And if this intersection is small, then the error we make is also small if we just add P of A plus P of B. So that is the union bound. And in the general case, if we have a sequence of events, so if we have n events AI, we can say that the probability that either event AI occurs is smaller or equal than the sum of the probabilities of the individual events. And the union bound is very useful if this probability in the top, this one is very difficult to calculate. If P of A and B is difficult to calculate, then we use the union bound. Okay, so now we come to the last tool that we need. That's the law of large numbers that you may also know from probability theory course or from Wahrscheinlichkeitstheorie. So the law of large numbers states that we have a sequence of independent and identically distributed random variables, xi, sequence, and they are independent and identically distributed. The expected value of xi is equal to mu. And then the law of large numbers says that if we take this sample mean, just calculate the average of xi to xn, 1 over n times x1 plus x2 plus x3 and so on. When n goes to infinity, then this value is equal to the expectation of xi. So this is equal to mu. So this average approaches mu. So essentially, the way you can prove it is using the Markov inequality. If you are interested in looking at the proof and how you can use the Markov inequality, we'll not do it here, but I will refer to the Wikipedia page, and that's it. So the law of large numbers, to summarize, states that the empirical average, sum of xi divided by n, of independent, identically distributed random variables is close to the expectation for large values of n. Essentially, there is a strong and a weak version of the law of large numbers, which essentially denotes the mode of convergence. So we can precise it a little bit, but we'll just use the general statement without looking into the details of convergence. The details get technical for the higher level understanding of why we need it. It's not so important. So we neglect the difference of the mode of convergence. So now we can move to looking at the maximum likelihood decoder again. So we have a channel output the channel output y consists of random variables y1 up to yn. We know that the code word has n letters. For each letter, we have a random variable y1, y2, y3 up to yn. Now, the decoder essentially computes or maximizes the, we like to start from maximizing the a posteriori probabilities. So we maximize p of x given y. And we do this maximization for every possible code word. And then we have seen that if we're looking at Bayes' theorem, then we apply Bayes' theorem, we get the likelihood here times the prior probability p of x, so that we probability that we select a certain code word, divided by p of y. And again, p of y doesn't change if we maximize over the code words. So this factor is always the same for the maximization. So we can leave it out of the maximization. It will not change the value of x that maximizes this expression. So this is the maximum of p of y given xi times the probability of p of xi. And then we assume that the probability that x is equal to xi is 1 over m, which is equal to 2 power minus k. So every code word is selected with the same probability. And this makes sense if we'll assume that the input bits to our decoder, they happen with, they are also happening uniformly 0 and 1 with equal probability. So every bit pattern happens with exactly the same probability. So we choose each code word with the same probability, and then the maximum likelihood decoder is essentially this guy. So we maximize over all the possible code words, and we maximize the likelihood, which is p of y given x. So this is the maximum likelihood decoder, and this forms the basis of our investigation. So this is summarizing the maximum likelihood decoder. We select the code word that maximizes this likelihood. Now, the issue with the maximum likelihood decoder in practice is that if m is large, we need to calculate many probabilities, and we need to carry out the maximization over many probabilities. So in the course of the lecture, we'll see simplified decoders, and the maximum likelihood decoder is essentially the best decoder that we can have. So now what we do is we assume, without loss of generality, that we transmit x1. Why without loss of generality? Well, because the code words are randomly constructed anyways. So they don't have a specific meaning assigned to them. Every code word could be different. So we just assume that we transmit x1, and now we calculate the probability that the maximum likelihood decoder produces an error. That's what we do. So we assume x1 is being transmitted. What is the probability that the maximum likelihood decoder produces an error? So let's take a look. So when does the maximum likelihood decoder produce an error? So we have a maximum likelihood decoder, and it decodes to the wrong code word. And it decodes to the wrong code word xm. And m goes from 2 to capital M. So again, we transmit x1, and we make an error if the decoder decodes either x2, x3, x4, x5 up to xm. So that's the wrong code word. So when does this happen? This happens if and only if. So if there exists an m in the set from 2 to m, such that the probability that y given x equal to xm is larger or equal than the probability that x equals x1. Then the decoder makes an error. So if there exists a certain code word or a certain m, such that this probability is larger than the likelihood of p of y given x1, then we make an error. We decode to that one. So now we introduce the event em. So we denote the event em and this is the event that the probability p of y given x equals xm. We have an index lowercase m, that's for very specific code word. It's larger or equal than p of y given x1. So it's the probability that for a very specific m, the likelihood is larger than probability that x of y given that x1 has been transmitted. Of course, in this case, we will make an error because we have a likelihood that is larger than the likelihood for x1. So we will make an error. So what we do now is we compute the probability that the event em occurs, which means the probability that the decoder may decode to the wrong code word xm. So I specifically put may here because it's not clear. So when I say it's the probability that event em occurs, it's not sure that the decoder also decodes to xm. There may be multiple m where this event occurs. So this may not be the only m where this is larger. There may be an m prime where this inequality is also the case. And then it depends if p of y given xm is larger or p of y given xm prime is larger. Depending on which one is larger, the decoder will either decode to m or m prime. It will not decode to x1, but it will decode to m or m prime. So it may decode to the wrong code. But now we assume we calculate the probability just that the event em occurs. We're only interested in this event em, which is given by this probability. So em is the event that p of y given xm is larger or equal than p of y given x1. So calculate the probability that event em occurs given that we have received y and that x1 has been transmitted. This is what we know. em occurs, y and x1 have been transmitted. So the probability that event em occurs is the probability, and now it gets interesting, that p of y given xm is larger or equal than p of y given x1. Given that y and x1 have been received. So now we calculate the probability that p of y given xm is larger than p of y given x1, given that we have transmitted x1 and we have received y. So now we have a condition here. So the condition says y and x1 are given. So this is essentially a constant. So this is essentially a constant due to the condition. Okay, so now we have the probability that a random variable is larger or equal than a constant. Markov inequality. What's the random variable? We interpret this probability as a random variable. So it's non-negative because it's a probability. Probability is a random variable that is non-negative because it never gets smaller than 0. Y is fixed, so this depends only on xm. So xm is the random variable in this case. So what we do is we apply Markov's probability, Markov's inequality. Markov's inequality says that this is smaller or equal than the expected value of x divided by the constant. So alpha. Again, Markov's inequality says that p of x larger or equal than alpha is smaller or equal than the expectation of x divided by alpha. So alpha is the constant, and this is p of y given x1. And in the numerator, we have the expected value. So we have the expected value of p of y given xm, given that we have received y and x1 has been transmitted. Okay, so now we can essentially simplify this term, and we simplify by just inserting the definition of the expected value. So we call the expected value of f of x is the sum over all f of x times the probability of x. And that's what we are going to do in the next step. So in the next step, we're going to calculate this probability. So we are going to look at this. We have this expression. So let's put it that way, and let's put what we had in the slide. That was unexpected. Sorry for doing this. And this is a little bit. Just put it up here so that we know where we can continue from. Let's just use this, guys. Okay. So we use the definition of the expected value to simplify this term. Okay. So we have the probability that event EM occurs given y and x1. This is smaller or equal than the denominator stays p of y given x1. So now the numerator. And we insert the definition of the expected value. So we use the definition of the expected value and get a numerator which is the sum over all possible xm from the code. And we have the f of f of x. F of x is the probability that we have received y given that xm has been transmitted, times the probability that xm occurs. So times p of xm. Okay. Now we can simplify this term. So we see that this is p of y given x times p of x. Our good old friend Bayes comes into play now. And we can simplify this using Bayes' theorem. And we just have and let me just use a little bit more space. So this is the sum over all x m from the code. And then we have p of x equals xm and y, the joint probability, divided by p of y given x1. So now what we have is we have a joint probability, and essentially we marginalize over xm. So we have the probability that x is equal to xm, y, and we sum up over all possible xm. This is the law of total probability, and from the law of total probability, this is nothing else as p of y divided by p of y given x equals x1. Okay. So we have simplified this, and we can summarize that the probability that the event EM occurs given y and that we have transmitted x1 is smaller or equal than p of y given divided by p of y given that x1 has been transmitted. So this is the first intermediate result that we're going to need. So again, what we do is we'll copy this result, and we're going to need it on the next slide. So inserting, and again putting this on top here for later reference. We can now calculate the probability that we make an error. Now we calculate the probability PE that the decoder decodes the wrong code word. And this is, we call it PE, and this is PE essentially, but it's conditioned on the fact that we transmit x1 and we receive y. So I put it under some condition. And this is essentially smaller or equal than the probability that either of the event EM occurs. So it's a probability smaller or equal than the probability that event E2 occurs, that event E3 occurs, or event E4, or any of those other events. So given that x1 is transmitted and y is received. So if any of those events EM occurs, then we possibly make an error. So why is this? Why do we have smaller? Why it's not equal? Why is there a smaller or equal here? That's because of a very, it's a technical detail. And for this, we go back to the definition of the event EM. We're looking again at the definition of the event EM. The probability that this guy is larger or equal than the P of y given x1. So they could potentially be equal. So an event EM could occur, and the two likelihoods are equal. What do we do in this case? We don't know if it either xm or x1 is the more likely code word. So we toss a coin, and with a 50% chance, we pick either xm or we pick x1. And that's why we only make an error in half of the cases in this case. So we may make a correct decision even if one of those events EM occurs. Just for keeping things simple, we have here larger or equal, because we didn't want to work with strict inequalities, but it doesn't matter for the final result essentially. So that's why here we have smaller or equal. So potentially, even if one of those events EM occurs, we make the right decision because they are equal. But in general, if one of those EM occurs, we make a mistake. Or it's very likely that we make a mistake. So if either of those events occurs, then we make a decoding, possibly make a decoding error. So now we have a union of events, and we don't want to calculate the probability that event E2 and E3 occur at the same time. That's going to be quite difficult. So we're going to use the union bound. So this is smaller or equal than by the union bound. Then the sum from m equals 2 to capital M of the probability that event EM occurs, given that we have received y and that x1 has been transmitted. So this is just the union bound. Now we see this probability, we use this bound here. And we also see that the probability that a certain event EM occurs is actually independent from M, because of the way we constructed the code. We use this random construction. Because of this random construction, we can assume symmetry arguments, and we get that all EMs happen with the same probability. We can also look at it from another perspective. We can insert this. We can insert this guy first. We see this guy doesn't depend on specific xm anymore. So let's do it in this way. So this is smaller or equal than the sum from 2 to capital M of P of y divided by P of y given x1. Okay, we don't depend on M anymore, so we just add up M minus 1 times the same expression. This is equal to M minus 1 times P of y divided by P of y given x1. We don't like M, so we replace M minus 1 by M. It's just M minus 1 is smaller or equal than M. So it's M times P of y divided by P of y given x1. And now we rewrite this a little bit. So we use the fact that we know that the rate of the code is k divided by n. This is equal, k is equal to log 2 of m divided by n. So we can rewrite m being equal to 2 power n times the rate of the code, 2 power nr. That's just a different way of writing m. So we're going to do this, and we say that this is equal to 2 power n times the rate, and times 2 to the power, now we write this as n times 1 over n times log 2 p of y divided by p of y given x1. It's just rewriting. So we want to put this into the exponent. It's 2 to the power log 2. And then we just expand this by n times 1 over n. We're going to see why we're going to use this. So again, this is turning out to be the important part, and this is what we're going to simplify next. So again, for take this over to the next slide, and this is what we had. And essentially, if we write down everything, we had that PE given XY is smaller or equal than 2 to the power NR times this expression. So now we're going to simplify this expression, and we're going to look in particular at this yellow term. And we keep this one just as a reminder where we stand. So we have this expression 1 over n times log 2 p of y divided by p of y given x1. And now we apply the property that we have a memoryless channel. So we have a memoryless channel. Memoryless channel means p of y given x can be written as the product from 1 to n of p of yi given xi. And from this, it also follows that p of y is equal to the product from 1 to n of p of yi, p of yi. It can also be proved very simply if we start from this term by just applying the chain rule of conditional probabilities and then just inserting the different values. Then you can easily prove this fact as well. So we're going to insert these facts for the memoryless channel. So again, we assume that here we have a memoryless channel. So this is 1 over n times log 2 of probability from 1, or the product from 1 to n of p of yi, divided by the product from 1 to n of p of yi given x equals xi equals xi1. So now we have the logarithm of products Very nice. We can put the product in front of the logarithm. It becomes a sum. So this is 1 over n times the sum from I going from 1 to n of log 2 of p of yi divided by p of yi given xi1. So now we just flip the term. So we put a minus in front. So this minus 1 over n, sum from 1 to n of log 2. Now we need to change numerator and denominator. So this becomes p of yi given xi1 divided by p of yi. And now we apply again our good friend Bayes' theorem. So according to Bayes, p of y given x is p of y, the joint probability of p of y and x, divided by p of x. So we apply Bayes' theorem. So this is with Bayes. Log 2. We have probability of xi and yi. I'm writing it in this way. Divided by p of yi and p of xi. So yeah, now this has a very nice form. And now we have something. We see we take an average. We take an average over this expression. And this expression essentially is IID distributed. We have xi, yi, and this is the probability that is certain. Remember, we have the random code. Everything is based on the random code. And now the random code comes into play. This is p of xi. This is the probability that we put a certain letter into the ith value. And then we're just looking at those at the realization. And this is the probability of a certain letter. So now what we do is we apply the law of large numbers. So now we say that this converges to, using the law of large numbers, to minus, still have a minus sign. I'm sorry, I want it black. Minus the expectation of log 2 of p of x and y divided by p of x divided by p of y. And I don't use an index I anymore because every letter is identically distributed. An identical distribution. So we can also write this. This is equal to minus the sum from j going from 1 to v, cardinality of the input set of the channel, then the sum from L going from 1 to W, the output cardinality of the channel. So recall that V is the cardinality of the channel input set, W is the cardinality of the channel output set. Then we have the probability that X is equal to Xj and Y is equal to Yj times the log 2 joint probability that X is equal to Xj and Y is equal to Yj divided by the probability that X is equal to Xj and the probability that Y is equal to Yj. Okay. This term should look familiar. If you recall Communication Engineering 1, or if you recall Applied Information Theory, this term looks extremely familiar. What is this term? This term is nothing else as the so-called mutual information. So we say that, or we define this term to be the quantity I of x, y, or the mutual information between x and y. And this is going to be very important. So what we have done is we have related the probability of error after maximum likelihood decoding with this expression. And this expression is nothing else as the mutual information of the channel, or the mutual information between the two random variables of x and y. So let's take a look at what we have again. So again, I'm going to copy this expression, and we're going to insert this expression, or again as a reminder. So where do we stand? What do we have? So we have the probability of error given x and y is smaller or equal than, we start 2 to the power n times r times 2 to the power n times 1 over n times the log 2 of p of y given p of y divided by p of y given x1. So, and this, by the law of large numbers, converges when n goes to infinity, converges to 2 power n times the rate r times 2 to the power minus n times the mutual information between x and y. We recall we have the minus sign, and we just simplified this yellow term converges towards the mutual information. So this is equal to 2 power n times the rate of the code minus the mutual information between x and y. This is the expression of the conditional error probability. Very nice expression. Now we can dissect this expression a little bit. So what we can do is we can look at two cases. Looking at the first case, case 1, the rate of the code is smaller than the mutual information between x and y. So in this case, that means that we calculate the rate minus the mutual information. This is going to be negative. So we have 2 to the power n times something negative. So if n is very large and this is negative, this term will go to 0. So 2 to the power minus n, because 2 to the power minus constant times n will go to 0. So we can say that PE of xy is smaller or equal than 2 to the power n times the rate minus the mutual information. This term is negative, so this guy will go to 0. So that's very interesting. It means that if the rate is smaller than this mutual information, the error probability goes to 0 with our maximum likelihood decoding as n increases. Very nice. So in this case, we have an error probability that goes to 0. So negligible error probability. Then we look at the second case. The rate is larger or equal than the mutual information. In this case, the rate minus the mutual information larger or equal than 0. So then the conditional error probability is smaller or equal than 2 power n times the rate minus the mutual information. And now this is larger or equal than 0. So it means we cannot say anything. This term will go towards infinity. And we only can say that the probability of error is less than infinity. Not so insightful. If you have a probability of error that's less than infinity, it can be anything. So we cannot, unfortunately, we cannot say anything here in this case. But if the rate is smaller than the mutual information, then we can say for sure that the error probability converges to infinity. So what we have to summarize is that the rate of the code is equal to n, and we have a rate of the code, and we have bounded the conditional error probability, so that's the error probability p of x and y, which is smaller or equal than 2 to the power n times r minus the mutual information. And if this rate minus the mutual information is 0, then the error rate can be arbitrarily small if n goes to infinity. If the rate is larger than the mutual information, we cannot conclude anything. So in the final step, we were a little bit sloppy. So what we did is we assume that the law of large numbers holds and that this expression that we had, in particular meaning this expression, converges to I of x and y, so the mutual information between x and y for sufficiently large n. And then we get an expression where n goes to infinity that still contains n. So this is a little bit weird, but it means that for a large enough n, we approximate this particular expression. So we can formulate this in a more precise way. So for what we would like to know, this is sufficient. So we know that the error probability is upper bounded as 2 to the power n, the rate minus the mutual information between x and y, or at least approximately upper bounded. And in the next slide, we are going to formalize this a little bit using the formula definition of the law of large numbers. And this is also included in the reference. So let's formalize it. And therefore, we're going to an empty page again. And the formalization works by starting from our expression. So we start by noticing that PE, so the probability of error, given that we know x and y, is upper bounded by 2 to the power n times the rate times 2 to the power n times a, where we apply the law of large numbers on a. And a, what is a? A is just an abbreviation because I'm a lazy person and I like to not write too much. So what we do is we apply the law of large numbers, the LLN, onto a. So a is 1 over n times log 2 of p of y divided by p of y given x equals the first code word x1. And we said that this will converge to minus the mutual information between x and y, or I of x and y. So what does the law of large number tell us? The law of large numbers says that for any epsilon and delta larger than 0, so we can fix two constants, epsilon and delta, they just need to be positive. So for any epsilon and delta, there exists an integer n such that the probability that a, the difference from a to minus the mutual information between x and y, that this difference is larger than delta, is smaller or equal than epsilon. So it means that we can fix some delta and epsilon. There is an n. N is included in this expression here, such that the probability that the difference between a and the value it converges to minus the mutual information, that this one is larger than delta, is smaller or equal than epsilon. So we can make a small drawing. So here we have, on the x-axis, we have a, and here we have minus the mutual information between x and y. And the probability that, so first, let me do it the other way. What we can do, well, we can say first the probability that A lies outside of this region is smaller or equal than epsilon. Now, we are not so much interested in the probability that we are outside of this region. We are interested in the probability that we are within this region. So we can also say that the probability that we are within this region so probability that A minus the mutual information between x and y is smaller than delta in absolute value is larger or equal than 1 minus epsilon. So there is the bulk part of this probability is included in this small region, and only some epsilon is outside of this region. Now we don't like absolute values. So what we like to do next is we're just looking at the case or the probability that we are below minus the mutual information plus delta. So this point here is minus the mutual information plus delta, because this region here is 2 times delta wide. So we have for mutual information minus mutual information minus delta, and minus mutual information plus delta. So this blue line is minus the mutual information plus delta. And we are interested in the probability that we are smaller, because we want to get rid of the absolute value. So the probability that A is smaller or equal than minus the mutual information plus delta. So I just got rid of the absolute value and I added delta. So this is essentially this blue region. We know the red region is larger or equal than 1 minus epsilon. The blue region must be larger, because we take the red region plus something more. So this also is larger or equal than 1 minus epsilon. The whole region that is over here, we don't care about that one, because that one is already negligibly small. So we just assume that because this one is already larger than 1 minus epsilon, and epsilon can be made as small as possible. So we just assume that we ignore this and it will be even larger. Okay, so now we can go ahead. Now we would like to calculate the error probability PE. So I would like to calculate PE, and PE is nothing else as the expected value of PE given X and Y. So the error probability that we calculated before was for a specific X and a specific Y. We want to know the error probability for all possible combinations of X and Y, so we take the average value, the expected value. So this is the sum over all possible realizations of X, the sum over all possible realizations of Y, times the joint probability that this X and Y occurs, times PE given X and Y. So now we can rewrite this as, again, the sum over all possible X, all possible Y, times still probability of X and Y. So this was the definition of the expectation. And now we make a distinction. So we add the identity function that A is smaller or equal than minus, so this is an A, minus the mutual information plus delta plus the indicator function that A is larger than minus the mutual information plus delta times PE of X and Y. And this allows us to split this whole thing into two sums. So what does it mean? And we can take a look at this. We can visualize this. So we have this space here, this box that I draw. That's the space of all possible X and Y. And I'm looking at A now. So I have a region for this X and Y's where A is smaller or equal than minus the mutual information plus delta. So these are all the possible X and Y's. And maybe let me draw this a little bit larger even, because we know that this is the main. So it's all the possible space of points, X and Y, where A is smaller or equal than minus the mutual information plus delta. And we know that this guy, or this region, is has a probability that is larger or equal than 1 minus epsilon. And the remaining term is what is outside of this. So we can write this as a sum over all possible X over all possible Y, P of X and Y, times the indicator function that A is smaller or equal than minus mutual information of X and Y plus delta, times P X Y plus the sum over all X and Y times the indicator function that A is larger than minus the mutual information between X and Y plus delta times PE times, and here I need to add the probability of X and Y times PE given X and Y. Okay, so now I have two sums. I have a sum over the green region. So this sum is over the green region. Let's mark it green. And this sum is over the red region in my plot. Okay. So now what I can say is that in this region where I am, in the green region, I know that A is smaller or equal than minus the mutual information xy plus delta. So I can put an inequality sign here, and I will write this in green, because that's the green part. So I sum up over all possible x, sum up over all possible y. I have the probability between x and y times the indicator function that A is smaller or equal than minus the mutual information plus delta. And now I can insert, because I know that PEXY is smaller or equal, that's where we get the inequality sign, 2 times n to the power r minus the mutual information between x and y plus delta. I just inserted the bound, because I know that PEXY is smaller or equal than this term, and I know that A is smaller or equal than minus the mutual information plus delta. So this is what I inserted, then I get this term. So now I have this guy, so I write this in red, x and y. We have the probability between x and y, the indicator function that A is larger than minus the mutual information plus delta. And now we have PE given xy. So we could insert PE given xy, but we know what it is, because we cannot say anything about A in this case. A could be larger than this, so we don't have an upper bound on A. So that's a little bit sad, because we cannot properly bound PXY. So how can we bound this? Well, we know that PE of xy is upper bounded by 1. It's an error probability, so it must be smaller or equal than 1. We just say that it is smaller or equal than 1, because we can say PE of xy smaller or equal than 1. Oh, there we go. So PE of xy smaller or equal than 1. This is what we insert. Therefore, we get a 1 over here. So now we see that these terms, they are no longer dependent on the summation, so we can put them in front of the summation. So let's just rewrite this a little bit. So this is 2 to the power n times the rate minus the mutual information plus delta times this green region. So it's the sum over all x over all y, such that A is smaller or equal than the mutual information plus delta times PE x and y plus, and then we have the red term, x, y, P of xy times indicator function A is larger than minus the mutual information plus delta. So we now know that this region is larger or equal than 1 minus delta. So this probability is larger or equal than 1 minus delta. But for us, it is sufficient to just say we carve out a region here. It has a probability of exactly 1 minus epsilon. we don't care about the rest. We just take a region of this green part that has probability of exactly 1 minus epsilon. And this probability will be the probability that we are in this region will be 1 minus epsilon. So this will be a probability that is larger than 1 minus epsilon, but we just restrict ourselves to a set 1 minus epsilon. That is a smaller probability than this one. This one is larger than 1 minus epsilon, but we are satisfied by just taking a region of 1 minus epsilon, and our inequality is still fulfilled in this region. So we can say that this is smaller or equal. We take a portion of the probability that is 1 minus epsilon times, and then we have 2 to the power n r. Let me use black color for that guy because that one is not in the probability, that's just a constant. 2 to the power n r minus the mutual information plus delta. And we have plus the remaining the probability of the remaining region will be epsilon. And here we just, this is exactly the probability that we are in the red region of the space. That's the probability that we are in the red region of the space. This one is smaller than epsilon, but we can make it larger, so we increase the size of the probability and we multiply it with 1. So this is plus epsilon. Let me make this in beautiful red color. So this is epsilon. So what we did is we essentially took the probability of this green region, and for each of those x and y's in this green region, we multiply with this upper bound. And now we took a smaller portion of this, multiplied with the upper bound, and the rest we multiply with the worst possible error probability, which is 1. So, and in this case, we have epsilon as an error probability over here. So that's what we do. And therefore, we have this inequality that we get finally. So now we can say that the error probability is upper bounded by 1 minus epsilon times 2 to the power n times the rate minus mutual information plus delta plus some epsilon. And this holds for any epsilon and delta, and then we have a specific n for which this one holds. So what this means is we can make delta and epsilon very, very small, then this term vanishes, and this term gets close to 1, and we have an n that is sufficiently large so that we converge to the result that we had before. So we can say that this will converge when n goes to infinity. It will converge to 2 to the power n times the rate minus mutual information plus without the delta. There we go. And that's how we can formally show that this result. We have that this probability of error, and now since we have formalized this, we can remove P of the condition on x and y. We have a probability of error PE that goes to this expression. And if the rate minus the mutual information is negative, the error rate can be made arbitrarily small. So now we can formalize this as a theorem, and that's essentially Shannon's channel coding theorem. So the channel coding theorem says that we have a code C with m code words of length n that are chosen randomly over the channel input alphabet. We have a rate of the code, which is log 2 of m divided by n. And now for a memoryless channel, if the rate is smaller than the mutual information, with maximum likelihood decoding, the error probability can be made as small as possible if the length n goes to infinity. And then we can use a term that says the rate is achievable. We have an achievable rate because we can make the error probability vanishingly small if n goes to infinity. So this was a very simple proof of the channel coding theorem. And immediately we have a few questions. The first question, what happens if we don't use maximum likelihood decoders, but simpler decoders? And essentially, we can also show that even with suboptimal decoders, we can reach a rate of the mutual information with significantly lower complexity. So we will see that there are codes where this theorem also holds with suboptimum decoders. Now, what happens in the second case if the rate is larger than the mutual information? Then we cannot conclude anything. So does it mean that possibly if the rate is larger than the mutual information, do there exist codes with a vanishingly small error rate? This theorem will not tell us. No way that we can say with this theorem because we have a very loose bound. We can just say the error probability is smaller than infinity. That doesn't help us. But there is a rescue. There is the so-called converse of the channel coding theorem. And that says that we're not going to prove it. That's related to applied information theory lecture. So converse of the channel coding theorem says that we have a memoryless channel and a code C that has m code words. If the code has a vanishingly small error probability, then the rate must be smaller or equal than the mutual information. So it says that if the rate is larger than the mutual information, there is no way that we can find a good code with a error probability that goes to 0. And even it has been shown that the error probability goes to 1 if the rate is larger than the mutual information. That's the so-called strong converse of the channel code. So the mutual information gives a very sharp bound on the rate of the code. So if the rate of the code is smaller than the mutual information, that means we can achieve an error probability that goes to 0 if n goes to infinity. If the rate is larger, on the other hand, than the mutual information, we cannot say anything. Or we can, according to the channel coding theorem, but according to the converse of the channel coding theorem, we say that the error probability should go to 1. There is no way that you can decode. So this is a very sharp threshold. So either you are below the threshold, then with a code of very large lengths, you can achieve an error probability that is small. If we are on the other side, so if the rate is larger than the mutual information, no chance. You cannot decode. There's no way that you can decode with a small enough error probability, even the error probability goes to 1. So what is this mutual information? And this vector has a core role in information theory. It's very important, not only in information theory, but also in machine learning where it's used and in also many other areas of where we consider information. So information theory really tells us how we can calculate this mutual information and what its meaning is. And all of this in communications is built on the channel coding theorem, which says that the rate of a code must be smaller than the mutual information, then the error probability will go and converge towards 0. So this brings us to an end of this quite long subsection, and in the next subsection we are going to look in information theory in more detail.